All right. All right, so how do we go about deriving these equations? They look kind of complicated. They're not too bad, but what we can do is we can start by considering the progress of the reaction along a reaction coordinate. What do we mean by that? Well, we can think about a reaction going along a path. It's starting out as reactants and then proceeding to a product at some point. And so by looking at the path as it proceeds from reactant to product, we can describe our process this way. And let's take our favorite example, iron 3 plus an electron going to iron 2 plus. Now at equilibrium, we can think of the iron 3 plus and iron 2 plus having the same free energy. So if we drew a path between iron 3 plus and iron 2 plus, often what they'll do is they'll draw this sort of overlapping curves, where the first curve is indicating the progress iron 3 would have to get to be made into iron 2. So we have to increase the free energy to some apex, some point on the curve, and then that free energy will then decrease. Why does it have to be? Of course, we have to have some sort of barrier, otherwise there's no difference between iron 2 and iron 3. So there has to be some barrier for interconversion, otherwise there wouldn't be separate species. So what is that barrier? Well, that barrier is, well, we can think of going in this direction as a reduction, as always, and going in the reverse direction as an oxidation. That barrier is what they call the activation energy for the system. Right, very well. Activation energy. And when the molecule is right at that particular apex, it really doesn't exist as a distinct species, but people will call that species the activated complex. In other words, we can think about at that point as being sort of a never-never land. It's got characteristics of both iron 3 and iron 2. It's halfway between going in either way. And at that apex, the activated complex, we can think of that species having no real direction of movement. It can fall back to iron 3 or go forward to iron 2 on that system. So that's the potential diagram for a system at equilibrium for a reduction-oxidation process. What can we do that's very interesting in electrochemistry is we can change the free energy of our system. Okay, we can change the amount of free energy that we've got available to the system by changing the potential. How can we do that? Well, if we put in a more negative potential, than the equilibrium potential, what we see is that those curves will shift. And now it's much more likely that we're going to be ending up with iron 2 plus than iron 3 plus. So the net flow, as soon as we have enough energy to get over that barrier, is going to be to iron 2. So it's easier to go to iron 2 than back to iron 3. On the other hand, if we have a more positive potential, the opposite will occur. And it's easier to make iron 3 plus than iron 2 plus. So a nice thing about electrochemistry is that's really interesting is that we can change the free energy simply by turning a knob on our instrument. We can change delta G the free energy that's available to a system simply by changing a knob on our potentiostat or our electrochemical instrument. And that's something you really can't do very easily with a homogeneous process. You can change the temperature and you can change some other things, but with electrochemistry you can just change the knob, we can change the free energy. So we can change the relative energies involved in the overall process. Okay, I think on your notes I want to point out something that on page EC3-3 that shows iron at the bottom. There's 3 in a row there. There's iron 3+ to iron 2+, where it says more positive than equilibrium. That should it says 2+ to 3+. It should actually be 3+ to 2+. I don't know if you see that or not. Page EC3-3. The bottom of those 3 on the right-hand side, you see it goes from 2+ to 3+, but it should be 3+ to 2+. All right, let's redraw that curve that I've shown here. Let's do it a little bit more detail. Let's take a look, and I think what I'll do is I'll just show you this curve, and maybe if Rob can zoom in on it a little bit, we'll just point out some things that we've got here. Can we zoom in a little bit, Rob? Okay, that's good. All right. So this is, you got this in your notes basically, and it's in the book, so you really don't have to bother drawing it again. I just want to show you what's happening. Here is our diagram of the change in the free energy as we change the potential. Suppose we start with some system, let's call it O to R, that has some electron transfer process. Now initially we might suggest that the shape of those curves, in other words, as we go along the reaction coordinate where O is converting to R by an electron transfer process, as the reaction tends to occur, the free energy of the system increases to a point at the activated complex point and then decreases again. There is a activated energy for that process for the O going to the activated complex point, and you see that's delta G double dagger. For the initial potential for the cathodic process. In other words, we're talking about a cathodic process as O goes to R. And so that's the terminology we're looking at. So that energy, the dagger, double dagger energy is the free energy to get to the activated complex energy. So we need at least that much free energy to get that molecule to be reduced, to get over that activation energy. On the other hand, the reduced molecule, you can see the free energy to get to the activated complex is much larger. So to go back, we need much more energy to get back to the O form in this particular case. Now, let's now change the free energy of our system by changing the potential of the system. Let's make the potential more negative. And what happens is that, actually more positive, and what happens then is that that dashed curve is the new potential that we observe, all right? And so now what happens, notice that the activation energy for that new potential is changed, and the activation energy for the anodic process is also changed. The change you see is here. You can see that we've changed the activation energy for the cathodic process by this amount and the anodic process by this amount. And this is a critical point. What we've got here is these curves, and now the shape of these curves I've drawn is basically straight lines. And you'll notice that I didn't do a very good job of drawing those straight lines, but the fraction that the amount of energy that we've changed isn't the same amount as the activation energy for the cathodic and anodic process has observed. In fact, the amount of energy change for the activation energy is a fraction of the total amount of energy change that we've applied. And that's because those two curves don't intersect orthogonally, they intersect on a slope. And so we see as we change down like this, that change overall is a fraction of the total change that we've moved down. And that fraction is is shown here. The oxidation barrier shifts down by a fraction 1 minus alpha NFE, and the reduction barrier shifts up by a fraction alpha NFE. So the total amount of free energy change that we see is the sum of those two processes, and that's the alpha term that we're seeing in the system. So the alpha term is a symmetry factor, and it has to do with what the shifts in the barrier as we change the free energy in the system. Usually alpha is very close to 1/2 or 0.5. Alpha is always between 0 and 1 because it's a fractional value basically, and it can be 0.5 typically, but it can vary. For certain systems it can be 0.8 or even higher. What's that mean when alpha is not 0.5? Well, it shifts the amount. So in other words, as the alpha shifts away from 0.5, the fraction of energy, the change in the activation barrier for the cathodic process changes more than, say, the anodic process, or vice versa. And so the electron transfer now has an asymmetry in it. It becomes easier to transfer in one direction than the other. Okay. Okay, well that alpha is, that's a description of alpha. It's not a very very accurate on a microscopic level, but it's good enough to really kind of understand what alpha is doing for us. And so we'll see later a better description of alpha as we go through our calculations and derivations. All right, so we have some idea of the meaning of alpha. Now let's see if we can derive a better meaning for the K0 idea. And to do that, let's write down expressions for the kinetic expressions in an Arrhenius form. And you might remember talking about Arrhenius forms of kinetics in maybe freshman chemistry or certainly in P-Chem. And an Arrhenius form has a temperature dependence in the process, and so Kf has to be equal to a term we'll call A sub F E minus delta G double dagger for the cathodic process over RT. And K sub B is equal to A sub F E minus delta G double dagger for the A term, anodic process over RT. And so here you can see our terms for the activation energy. It's the amount of energy that we need to get over the barrier, whether it's an anodic process or a cathodic process. A sub F is a so-called frequency factor. And notice, as in all Arrhenius formulations, the rate constant is proportional to the 1 over the absolute temperature. As the temperature increases, the rate should increase proportionately. Again, we're using a sort of a semi-empirical description of kinetics. The Arrhenius is a semi-empirical description of kinetics in general, and we're using it for our particular case. Basically, all we've done is we've taken that energy that needs to get over the barrier from this way to this way, and that's a delta G double dagger for the for this is a let's see, how do we draw that? 3 plus to 2 plus. So that's a reduction process. So that would be delta G C in that particular case. All right. Well, we need to think about that a little bit more clearly, because we can't just leave it at that, because we can't measure delta G activation energy directly. We need to understand the kinetics, to do it experimentally, we need to have some other way of looking at the system. So we do that? Well, what we can do is we can change the formulation a little bit. Let's redraw it, let's rewrite it, and let's draw our forward reaction rate constant is equal to this frequency factor, exponential term, the nicest delta G double dagger, and then we'll put in a, actually, I think a better way to do that would be putting an I in here, because that's how I originally did it in the curve. And what we've done is we've separated our exponential terms into two fractions. Remember, we can take a delta G value and convert it into the activation energy and also then the activation energy change. And so the activation energy change is this part here. And that's just a delta G change. And so we can take that delta G and convert it back to electrical potentials or potentials. So the delta G change is just minus alpha NFE. And that should be obvious to you if you go back and look at those expressions. Whatever we've changed, we've just changed it by that fraction alpha, or minus alpha NFE. This part here is basically an independent of potential. And that's the standard activation energy. That, for example, is the potential energy at the standard reduction potential, or whatever we decide to be the standard point in our system. And so we're measuring the potential changes from that standard point, and that's that particular delta G for the initial system that we've got. Case of B is very similar. Let's call that A. Oh. Okay. Again, this is the change. Remember, that's a fractional amount of the total change in delta G, and that's that fractional component for both we're seeing here. Here again is our standard activation energy things. And so let's call this part here, for both systems, let's call that K0 in this particular case. And so Kf is equal to K0F E minus alpha NFE. In case of B is equal to K0B E 1 minus alpha NFE. Okay. So what have we done? We've just taken the same thing as before, but we've taken this part here of the Arrhenius formulation and lumped it all together into just one constant. Because it's independent of potential, all we need to do is figure out what that is, and that's all we need to know. So we put that in, and then we got a potential dependent part of our expression up here. Now let's take a special case. Let's make our bulk concentration of our oxidized species equal to the bulk concentration of the reduced species. Let's make our potential of the system be equal to the formal potential, also equal to the, since the CO and CR are the same, that will be the equilibrium potential as well. In this particular case then, Kf, there we go, sorry. In this particular case, since we're now at equilibrium, the forward rate velocity is equal to the reverse rate velocity. So as we already wrote down, Kf C0 star is going to be equal to Kb Cr star. And so that we can rewrite our expression like so. We see that K0 F E minus alpha NFE is equal to KB 0 E 1 minus alpha NFE, that's a small f, NFE, like this. And what we find out is that those two being equal is also equal to a term we'll call K0. And so K0 is that potential independent when in fact we're at the standard potential. So K0 sub f is for the forward rate and the K0b is for the reverse rate of the activation energies. But if we specify that K0 is that K0 is for the particular case when we're at the standard potential, then K0f, K0b is equal to K0 without a subscript. In other words, they're both the same. Because at that point Kf is equal to Kb, because C0 is equal to Cr star, and so on. Okay. So then we can rewrite our equations again, now including our new information about K0. So Kf is now equal to K0 e to the minus alpha NFE. K sub b is equal to K0 e to the 1 minus alpha NFE. All right, so these expressions are a special formulation, which we'll call the Butler-Volmer formulation. So they're very ubiquitous throughout electrochemistry, are these expressions for the forward and the reverse rate constant. Well, let's look at them again. We've got an expression that is dependent on the exponential form of the potential, which is what we want. And actually, I should rewrite this a little bit. Because we're specifying that we're actually at the E0, we have to include, let's rewrite this here. Why do we do that? Because we specify that we're actually going from a potential up here where we're at E, which is unspecified, to a potential that's reference to the standard potential, the E0 prime. So we'll substitute in the fact that we're referencing ourselves against that standard potential. So we have to include E minus E0 in that particular case. So again, we've got an expression that's an exponential function of potential. That's got that B term in there. It's not exactly a 1 over B, but you can see how that's a B term. And then we also have an A term. So that parameterizes our expression. And so if we plug in what the current would be, remember the expression we've had before, it'd just be this, NFA, K0, and okay, and that would be minus C sub r, x equals 0, E 1 minus alpha, NF E minus E0 prime. All right, so this one I want you to memorize. I guarantee you'll see it again. Okay, so here's our expression for the current as a function of potential. Now, again, what we've got for the current is, again, because the current is an indication of the net rate, the current does have a function of potential in here, and the current also has to be a function of the concentration of the species in solution, so we also have that in the system as well. Well, we're going to check that equation to make sure it's actually a valid equation. What are the things we check? Well, we already saw that it's got the proper exponential function, function of potential like we expect. What's the other thing we needed to verify? That was the Nernst equation. In other words, at equilibrium, it should decompose to the Nernst equation. So check for proper equilibrium behavior. So at equilibrium, what's the important thing? Well, we notice the net current is 0. Now, that doesn't mean the anodic cathodic currents may be not 0, but the net current, I, that we observe is going to be 0 at equilibrium, has to be. So we can rearrange our equation and get the following expression. We've just taken those terms and equated them to each other. Okay. And then we can also make the statement that at equilibrium, CO star is equal to CO x equals 0. What is that? Well, at equilibrium, if the concentration of the bulk isn't the same as the concentration at the interface, we wouldn't have equilibrium. So we have to have the bulk and the interfacial concentrations the same, otherwise it won't work. And the same thing can be stated for the reduced species concentration as well. So we can cancel out the terms and substitute in our expressions for the concentration at the electrode surface, and we see that we get an expression like this: CO star over C sub R star is equal to E NF E minus E0 prime. And we can take the logarithmic form of that and get this. And we've changed F back to the expanded form to see the normal form of the Nernst equation. Okay. So we've taken our experimental, semi-empirical, parameterized current equation, applied equilibrium conditions to it, and found that it has regained the Nernst expression. And so that's passed our second test. We've got the parameterized, this exponential function of potential. It's also equals the Nernst equation at equilibrium. Okay, I think now would be a good time to stop. So why don't we take a little break now, and we'll begin again in about 5-10 minutes.
Started converting, we're still in the little f there, and then
That's just a condition thing, is just a capital Let's continue. As we just showed you, we can derive the Nernst equation from our kinetic expression. Let's play around with our expression a little bit and get some different forms that may be of use to us as well. One very useful form is available to us when we introduce a new parameter. It really is a function of the K0 or vice versa. We can introduce a term called the I0 term, and that's what they call the exchange current. Now I0, the exchange, exchange current is given the term subscript 0 to indicate an equilibrium type process. And so just like K0 and delta G0 and E0, I0 is initially defined at equilibrium. But what I0 is equal to is the cathodic current component and equal to the anodic current component at equilibrium. Now remember, our net current is 0 at equilibrium, but just because we have a net 0 current does not mean that the components of the current, the cathodic and anodic currents, are 0. And so I0 is kind of like an idle speed. For very rapid reactions, we can imagine that IC and IA are both very large, but they've canceled each other out. Whereas for very slow reactions, net reactions, we can imagine that IA and IC are very slow at equilibrium, very small at equilibrium. So the larger I0 is, really the more facile the reaction is, the more easily it can produce current, and we get away from equilibrium. Okay. So I0 is, when we put it in, we can substitute in I0, and we find that I0 is equal to NFA K0 C0 star E to the minus alpha NF E equilibrium. Okay, so here we're substituting in at equilibrium, so we can take an equilibrium condition, and that's one branch of this expression that we've got above, and we've substituted in for that, and we can then take a previous expression, let's take this one right here, and raise it to the minus alpha power. And we get this expression for the ratio of the concentrations, the bulk concentrations at equilibrium. Okay, so let's redefine some terms. E0 prime is defined as the potential when C0 over CR is equal to 1. E equilibrium is the potential when C over CR is equal to any ratio but I equal to 0. All right, so that's two different potentials. E0 standard reduction potential specifies that the oxidized and reduced components are equal to each other and equal to 1. The ratio is equal to 1. Whereas the equilibrium, C over CR can be equal to 1, but specifically it's for the situation when the current through the cell would be 0, I equals 0. And so, again, let's rewrite our definition for the overpotential. And that's E minus E equilibrium. All right, so we're getting to what I wanted to get to in a minute here. Got all that? Let me just put it up here. So let's rearrange and rewrite our expression. We can rewrite our exchange current. Now we're substituting in what we've just derived to be equal to NFA K0 C0 star times 1 minus alpha CR star times alpha to the alpha power. And for the particular condition when C0 star is equal to CR star, we get a useful expression that states that exchange current density is equal to NFA K0 CO, or just call, let's just say C, and where CO star equal to CR star is equal to C. In other words, let's assume a particular condition when oxidized and reduced components are equal to each other. So you can see the relationship between the exchange current density and the standard rate constant. Let's rearrange things again. And substituting in now what we've seen here for the I0 and the expression for CO star and so on, we can see that I sub C is equal to IC, our standard exchange current, times the concentration of O at the electrode interface over the bulk concentration, times E to the minus alpha NF. And then we'll use eta now to indicate the potential dependence as the E minus equilibrium potential. And I sub A would be a similar expression. But E to the minus 1 minus alpha, or E to the 1 minus alpha, NF, and our eta. And again, moving things around, we can substitute all those values for I cathodic and I anodic, and we see that the current is equal to the exchange current times the concentration of O electrode surface over the bulk minus an expression for CR at the electrode surface, again E to the 1 minus alpha 1 minus alpha NF eta